Assalamu alaikum, dear students. Our today's topic is chemical kinetics, and today our main focus will be on rate of the reaction. Chemical kinetics is that branch of the chemistry which deals with the study of rate of the reaction or speed of the reaction. Number second, factors on which rate of the reaction depends. Number third, mechanism of the reaction. As we know that reactions have been classified into three categories. Number one, very fast reactions. Those reactions which take place instantaneously. These reactions are mainly of ionic nature. Example, silver nitrate reacts with sodium chloride, forms silver chloride plus sodium nitrate. This reaction is also known as double displacement type of reaction. Number second, very slow reactions. Those reactions which may take days or months to complete. Example, rusting of iron. Number third, reactions which are of moderate speed, neither too slow nor too fast. Example of these reactions, hydrolysis of sucrose and hydrolysis of ethyl acetate. One more example is decomposition of H2O2. In chemical kinetics, we mainly deal with the reactions which are of moderate speed, which means that those reactions which are neither too slow nor too fast. Rate of the reaction is the speed with which reactants are converted into products. Rate of the reaction can be defined as change in concentration of any one of the reactant or product per unit time. We can also say that rate of the reaction in terms of reactants and in terms of products. In terms of reactants, we can say that rate of the reaction is decrease in the concentration of any one of the reactants per unit time. And in terms of products, we can say that rate of the reaction is increase in the concentration of any one of the products per unit time. As evident from this graph, concentration of the reactant A shown in purple decreases with the time, whereas concentration of the product B, which is shown in green, it increases with the period of the time. Let's take an example. A gives B. As we say that rate of reaction can be expressed both in terms of the reactant as well as in terms of the product. A here is a reactant. For it, rate of the reaction with respect to A is change in concentration by change in time. Let's say that let A1 be the concentration at time T1, A2 be the concentration at time T2. Then change in concentration means A2 minus A1 by T2 minus T1. This is equivalent to change in concentration, change in time. Negative sign indicates the decrease in the concentration. as was evident from the graph. Decrease in the concentration of reactant with passage of time. For products, rate of the reaction can be expressed as change in concentration by change in time. Let B1 be the concentration at time T1, B2 concentration at time T2. Then change in concentration will be written as B2 minus B1 by T2 minus T1, which is equivalent to change in concentration, change in time. This equation and this equation, they are both known as average rate of the reaction. Minus of change in concentration of A, change in time, and plus of change in concentration of B, change in time. They are both known as average rate of the reaction. So rate of the reaction can be expressed either in terms of the reactants or in terms of the products. As we know that rate of the reaction is a positive value. In order to make it positive, we have to multiply this negative with minus 1 so that negative and negative becomes positive and we get positive value of rate of the reaction. For complex reactions in which the stoichiometric coefficients are not same, the stoichiometric coefficients are different in the reactant as well as on the product sides, how can we write the average rate of the reaction for such reactions? Let's take this example where it is written as the small alphabets A, B, C, and E, F, G, they are the stoichiometric coefficients, whereas the capital alphabets, they represent the chemical species. For such species, we can write the average rate of the reaction as decrease in the concentration by change in time divided by the stoichiometric coefficient. Whatever will be the stoichiometric coefficient, that has to be divided while writing the average rate of the reaction. For example, in this equation, we can write decrease in the concentration of A with respect to time divided by the stoichiometric coefficient. Similarly for B and similarly for C, we will write decrease in the concentration divided by decrease in time or change in time divided by the stoichiometric coefficient. Here the negative sign indicates the decrease in the concentration. Here the negative indicates decrease in the concentration. For C as well, it will be minus 1 by C, decrease in concentration of C divided by change in time. For product sides, we will write plus of increase in the concentration of E by change in time divided by the stoichiometric coefficient, that is E. And for F and G, it will be written as increase in the concentration of F divided by stoichiometric coefficient, increase in the concentration of G divided by the stoichiometric coefficient of G. Let's take another example. For example, we write 2 times Hi, hydrogen iodide, which gives H2 plus I2. Here the stoichiometric coefficient of reactants as well as products is quite different. For this, we can write average rate of the reaction as minus times 1 by 2 concentration of Hi divided by change in time. And for H2, we will write plus of H2 change in concentration divided by change in time. For I2, we will write plus times change in concentration divided by change in time. The units of the rate of reaction are mole per liter per second, because we know that rate of the reaction is expressed as change in concentration divided by change in time. For example, for a reaction A gives B, we write average rate of the reaction as change in concentration negative of LA divided by change in time. This change in concentration has the units of mole per liter, and this time has the units of second, so it comes out to be mole per liter per second. In case of gaseous reactions where the concentration is to be expressed in partial pressures, the unit comes out to be atmosphere second inverse. Since average rate of the reaction decreases with the concentration of reactant with time, as the concentration decreases, this average rate of the reaction also decreases. We can say that from the law of mass action, the rate of the reaction is directly proportional to the average concentration of the reactant. Since the concentration of the reactant decreases with the time, so the rate of the reaction does not remain constant throughout. If we have to calculate the rate of the reaction at a particular instant, that is known as the instantaneous rate of the reaction. This instantaneous rate of the reaction can be defined as a rate of the reaction or change in the concentration of any of the reactants or products at a particular instant of time. To express instantaneous rate of the reaction, we have to take small intervals of the time so that rate of the reaction remains constant. Similarly, if dt represents the small interval of time, then dx or dA will represent the small change in concentration. Instantaneous rate of the reaction will be written as dx divided by dt. This is instantaneous rate of the reaction at a particular instant. Rate of the reaction at a particular instant can be calculated from the graph. We have to draw the tangent to the graph and the slope of the line. Slope of the line gives us the instantaneous rate of the reaction. That slope is equal to tan theta. If we plot a graph for both these reactions, in order to calculate the average as well as the instantaneous rate of the reaction, we have to plot a graph between concentration and time. This is T1 and this is T2. Concentration of C1, concentration of C2. This is the graph for reactants. From this graph, we can calculate the average rate of the reaction as well as the instantaneous rate of the reaction. This gives us average rate of the reaction, which is equivalent to, in case of a reaction A gives B, this reaction average rate of the reaction is equal to change in concentration of A by change in time, and this slope gives us the instantaneous rate of the reaction, which is equivalent to dA by dt. From this graph, if you have to calculate the average rate of the reaction, average rate of the reaction can be calculated by change in concentration between any 2 points divided by the time taken. Similarly, for products, we can write this graph as concentration versus time. Concentration C1, C2, T1, T2, time T. We can calculate average as well as instantaneous rate of the reaction or products as well. This graph, this gives us the average rate of the reaction for products, which is equivalent to change in concentration plus divided by change in time. And from this we get a slope here. From this slope we can calculate the instantaneous, which is equivalent to rate of the reaction dB by dt. Hopefully you have enjoyed this video and we will continue it.